Good morning, everyone. My name is Siyu. I'm a PhD candidate in Penn State. Today, I will be talking about my second year research progress in Soar workshop following my last year's presentation. I will be continue discussing my work on transferring cognitive model knowledge of decision making into large language models. So those are the references that build up this work. They are the state-of-the-art literatures on integrating cognitive psychology with large language models and the classic literature on the common model of cognition and cognitive architectures. So today I will briefly talk about my research blueprint, the introduction, introduce a simple cognitive large language models, and talk about the following work on creating another cognitive LLM for complex decision-making tasks. So last year, the Soul workshop, I have been talking about my work on model human cognition with symbolic knowledge representation. Specifically, I talk about how I created a cognitive model using ActR to solve a decision-making problem in the context of manufacturing. And this year, following by last year's work, I will be, I will keep talking about build the cognitive large language models pipeline, then introduce the first simple cognitive LLM on a generative classification task, and my ongoing progress on building a more complex cognitive LLM in generative NLP tasks. So cognitive decision intelligence have drawn attention across academic and industry, spanning from decision support to augmentation to automation. Specifically in decision automation, the machine plays a larger and more proactive role in decision processes and handed over the result to the human for final judgment. In this research, I focused on to augment the decision augmentation part. So when we talk to the plant manager about using off-the-shelf large language model for decision making, there are always issues persist. For example, hallucinations, noise influence behavior, lack of trust, and bad predictions and increased risks. So that makes me thinking, what if we can create an assisted AI decision-making tool to augment AI decision-making with human cognitive understanding and reflect how humans perceive and understand the world through cognition and knowledge? Start from that, I start to look at the literature that relating cognitive psychology to human-like decision-making support tools. And there is an emerging body of literature that connect these two fields of study together. On the left-hand side, they use large language models neural representations in behavior psychology science research. And on the right-hand side, they use cognitive psychology experiments to align LLMs to the human-like behaviors. I bought this arrow direction because that's aligned with the method that I'm going to use in my research. Within those body of literature, there is a piece of work called Centaur that attracts my attention. Centaur is a foundation model trained on large-scale human subject data for psychology alignment. Despite its innovative approach to make a human-like alignment language models, it exhibits deficient. It is very data expensive and computational expensive. So for example, to make a Centaur, you need 160 psychological experience and in a total of 60,000 human subjects. And despite the size, it lacks the grounding in the metacognition because collecting metacognition in real human subject is always non-trivial. So that motivates me to think about develop human-like decision-making tools for medium and small-sized companies such as Bosch to fine-tune a large language models for domain-specific human-like decision-making tools. This is the current proposed solution to create cognitive LLMs. a decision-making problem was conceptualized. Such problem was used to build a synthetic cognitive agent using ACT-R, or you can use Soar. Such cognitive agent will be used to run stochastic in a large scale to generate human-like decision-making trajectories. And such trajectories will be reformulated into a data set. The data set will be transformed into the larger model through a developing knowledge transfer framework called LLM ACT-R. So I'll have a very short prime on the ACT-R. ACT-R is another kind of cognitive architectures implement modules of mechanisms of cognition. The core layer of ACT-R is called cognition layer, contains of production memory and declarative memories. The production memories gives you action rules, and the declarative memories encode the factual knowledges. It can be also associated with perception and motor layers and can interact with the environment. So for the first cognitive LLMs, the simple one, the prototype we've been putting into the manufacturing context. The decision-making tasks, for example, it can be production optimization. A production line consists of two sections with potential defector sources, pre-assembly and assembly. Pre-assembly takes 40 seconds with OEE rate of 88%. Assembly, on the other hand, takes 44 seconds and another OEE rate. So we asked the model to achieve a total assembly time reduction of 4 seconds, which section you need to identify to optimize. Such problem will be passed into cognitive LLMs, and ultimately we hope the larger model can generate cognitive aligned suggestions like the cognitive model. For our simple cognitive LLMs, as I introduced before, the context is a manufacturing decision-making. Product goes through from supplier to customer, undergoing several sections. Each sections have some metrics associated with it. So for the decision-making tasks, the decision space is being identified as vulnerable sections as pre-assembly and assembly. The probability model contains cycle time, overall effectivity rate, headcount cost, and the defector rate. The loss function is the weighted combined of increase the defector rate, race, and headcount cost. And the decisions we want the model made is to minimize. So I have a brief prime on the last year's conclusion on the cognitive model we built named VSM ACT-R. Such model extracted from the observed human behavior with different level of experts. It has 3 sets of experts, expertise level, intermediate level, and novel level, which has a corresponding set of production rules and decorative chunks. If multiple productions compete with expected utility values, the probability of selecting such production is calculated using softmax function. And the reinforcement learning realized in this model, realized through compounded reward function. The reward function takes 2 variables. One is the strategy used, i.e., which kind of strategy the model used to make the decision. Is it novice or it is expert? And another one is a cost evaluation function that evaluate how the model, the decision gonna have the effect on the headcount cost. Then the compounded reward will be propagated back to the sequential of the production rules to influence the robust learning and the next round of decision making. So with the model built and the data validated, the next step, we collect the model's data in a large scale. The data being collected comprised of 2 parts. The first part is a learned vector of decision-making steps of VSM ACT-R model. And the second part consists of numerically encoded reverse decision-making from VSM ACT-R model. To get the learned vectors, we pass each sentence or each steps of the decision making into a sentence transformer, and each embedding of each sentence gone through a dimensionality reduction, and reducted embeddings will be concatenated into a one-dimensional vectors. So this is an exemplar of using the first simple cognitive LLMs in manufacturing decision making. The input is the natural language prompt of the decision making, and the output is the numerical encoded decisions that maps to the cognitive models, human-like decisions. The crafted cognitive vectors I introduced before is passing into the forward passing of one layer of the residual stream of the language models to ideally elicit some cognitive inspired behavior population. The baselines, we compare to the pre-trained model, random guess model, and a fine-tuned model without the cognitive vector infused. The data set is decision-making trial simulated on the large scale. We use the held out data to assess the performance on unseen problems. The measurements is the goodness of the feet use negative block likelihood. The results shows the LLM ACT-R pipeline shows the cognitive LLM has a better perform than the pre-trained model and has a better perform than the random guess model. Specifically, if you see the negative log likelihood of the model with the infused cognitive vectors rather than without the infused cognitive vectors, you can see the one with infused cognitive vectors has a decreased mean values on NLL and has a decreased variance across 10 epochs of NLL compared to the one without cognitive vectors. So the main takeaway is it is possible to transfer human-like decisions from cognitive models to larger models through activation engineering during the forward pass and fine-tuning larger model with reinforcement decisions. The core is we still have this trustworthiness of the cognitive synthetic agent and the generalization. So the next step is toward creating a cognitive LM for a complex task. Think about if we have this out of distribution generalization issues, we have an expanded decision space, and we have a more complex probability model. So we need to update the transfer pipeline from human-like decisions in a numerical targets to transfer guided perceptions, memories, and goal settings. So I'm now working on this second cognitive LMs, which is a generative NLP model with an input of the prompt and the output of a natural language response showing trains of reasoning that reflect the procedural rule matching and the firing mechanisms of cognitive models. This is the current framework, and I'm thinking to develop this develop this cognitive LM. It will use agentic systems. These two maps are convey the same concept. The user will taking the prompt to interact with a Streamlit app. After Streamlit app takes the prompt, it will send the task request to agent manager. Such agent manager will be modularized to map the different components of ACT-R cognitive architectures. It will primarily comprise of the two types of the agents. One type of the agents will be declarative grounding agent, and then another type of the agent will be procedural advising agent. The function of the declarative grounding agent is to filter out the chunks and associated slots for such tasks. And such agent will be validated through a KG, a knowledge graph to be defined. The validated chunks and slots will be passed to a procedural agent that be validated by another validation agent to output the cognitive procedural rules that maps to the cognitive models. It will also have a human in the loop to validate the chunk and the slots that users can use to intuitively map their own chunks and the slots to match to their cognitive frame. I have a very simple walkthrough of the current development. The user submits the prompt and selects their cognitive frame. Currently, we support expert, novice, and intermediate. Next, the declarative grounding agent generates chunks and slots. The user can choose if you agree with this generalization or no. If no, you can edit the decorative chunks and the slots based on your own intuitions. Then the procedural rules will be generated using the procedure grounding agent. Such rules will be validated using another validation agent contains the repository of VSM-ACTR rule templates. To be continued, we want to implement knowledge graph and augmented retrieval generalization and tested on more open source language models. I want to acknowledge Bosch Center for AI, Drs. Alexandra Otorami and Jonathan Francis for the collaboration and continuing mentorship. Those are the related publications in case you are interested in our prior researches. Thank you so much.
Thank you. Any questions from people in the room? People online, if you have questions, please raise your hand. Andrea, go ahead.
I was clapping, but I'm happy to ask a question anyway. That was like an impressive presentation. I tried to generate code with the ACTR code with LLMs before, and I ran repeatedly into some problems. So I wanted to get a sense, how robust is this process? Maybe you have better prompts than I do. But when I give you like a list of chunk types and so on, there are always pieces where the model stops running. There are some subtleties in the way to make it run that LLMs seem to be unaware of.
Thank you so much, Professor Stockel, for this great questions. So first, this problem is conceptualized in this manufacturing domain, and we have previous built up this ACTR model called VSM-ACTR. Already have a set of production rules that has been tested, working really well. So for this approach, not only we crafted the system prompt and user prompt, but also we added a validation agent connected to the procedure grounding agent. And such agent specifically, we just give it a repository of the previous production rules that we created and validated from VSM-ACTR. So first, we give a very constrained problem here for language model. And second, we give them the hands-on instructions on what previous model works and what is a successful production rules look like in the two candidate decision-making problems. And your tasks are specific in just the build upon those prior knowledge and generate production rules that contains more decision candidates. And that significantly increase the successful rate of the production rule generating.
Well, thank you so much.
You're very welcome.